Ladies and gentlemen, class recording has started. So, yesterday we started talking about collisions, and we talked about the idea that because collisions involve two objects interacting with one another, applying forces to one another, those are forces are internal forces, so momentum is conserved in any collision. But depending on what happens to the kinetic energy of those objects, we can classify those collisions in one of two ways. And those two ways that we could categorize those collisions as either elastic or inelastic, where momentum is conserved in every collision no matter what. Kinetic energy is also conserved in an elastic collision, but kinetic energy is not conserved in an inelastic collision. And then we talked about one specific type of inelastic collision called a completely inelastic collision, where our two objects actually come together and become one object. We'll spend a lot of time today talking about that and analyzing it quantitatively, doing some calculations based on that. So let me do this first, because the screen is making me upset, so stand by. That did nothing. No, that's okay. And it didn't exactly do what I wanted it to do, but all right. So yesterday we said that the basic idea of solving any collision problem is to conserve momentum. And these three equations all illustrate conservation of momentum, increasing in more detail as we move down further. We will look at these and use these today when we start numerically analyzing these collisions. The first type of collision that we sort of started talking about yesterday was the completely inelastic collision, where the two objects stick together and become one object. We talked about these two railroad cars, one moving before the collision, the other one not moving, then they couple together. And we said that we could kind of take an educated guess and say, well, if this one's moving, if there's one moving here and now there's two moving here, because there's twice as much mass, there'd be half as much velocity, and we went through and we showed that in fact that is the case. But when we analyze the kinetic energy, momentum is conserved in that situation, but kinetic energy is not conserved, and we only actually end up with half of the amount of kinetic energy that we started with. That's not conserved, but that's what happens in that inelastic collision. Okay, good there. All right, let's take a look at this example problem here, example 7.10, the goal line stand. So it says, on a touchdown attempt, a 95 kilogram running back runs towards the end zone at 3.75 meters per second. An 111 kilogram linebacker moving at 4.10 meters per second meets the runner in a head-on collision. If the two players stick together, what is their velocity immediately after the collision? So, we've discussed on several occasions, if velocity and after show up in the same sentence, what is that asking us to solve for? Now, in this case here, because there is, hold on one second. Okay, sorry for that. So, we said if we talk about velocity immediately after the collision, it's asking us to solve for final velocity. However, in this problem, it says that the two players stick together, So how many final velocities are there really going to be in this problem? Just the one, because if they're stuck together, they both have the same final velocity. All right, other information. It tells us that the mass of the running back in this problem is 95 kilograms, that the running back's initial velocity was 3.75. The mass of the linebacker, 111 kilograms, and the initial velocity of the linebacker, 4.10 meters per second. All right, so two things before we get into solving this problem. First, there's one more thing that we have to include in our set of information here that's important when we're dealing with momentum, What does it tell you about? It says that gives you speeds, right? But we've discussed that momentum is a vector quantity, right? So, in this case here, what do we have to do with our two velocities? One's got to be positive, one's got to be negative. If we look at the arrow here that they gave us in the picture, they've called towards the right a positive velocity. That means that that one's going to have to be negative. Okay? Now, one other thing, this is not essential to doing the problem, but just to help us to see if we're on the right track. Based on the information that they gave us here, what would we expect to happen during this collision? They're going to have a negative velocity afterwards, right? Because the linebacker has more mass and more velocity, right? So he's going to have a greater momentum. That momentum being conserved means that if their momentum's together after the collision, should take them in the negative direction, right? So let's see if that's what we end up with. All right. Because this is an interaction, a collision, right? Momentum has to be conserved, so sigma pi equals sigma pf, okay? Before the collision, there are two objects, so we have to look at each of their momentums separately. But after the collision, we only have one object. And I know this is a lot of subscripts, right? But putting the two objects together, right? Running back, linebacker, all together, right? And that gives us the final momentum. And you don't have to show me every single one of these steps every time, but we know that when we're calculating momentum, right? Two things, we have to calculate the momentum of the object based on two factors, right? Those two factors being, how do we determine the momentum of an object? I guess that was mass times velocity, right? So we go mass of the running back times initial velocity of the running back plus mass of the linebacker, velocity of the linebacker initial. Over here, like we said, because they stick together, there's only going to be one object, right? Mass-wise, what are we going to have to do? If the two objects come together and become one object, what do we have to do when we're calculating the momentum? How do we get the mass? Just add them together, right? So mass of the running back plus mass of the linebacker times that final velocity. And when you go through and calculate, I believe you'll find that the only thing that we don't know in this situation is the final velocity. So go ahead and plug in things that you know and get ourselves an answer. Good. Okay, what I would probably do if I was solving this problem, I would just start plugging numbers into this equation, and then this would be the only unknown that I would have, and then I would go instead of trying to manipulate this equation and get just to get VF by itself, I would just plug numbers in and solve for the variable. So. All right, are we okay with this? Sorry, do we need a couple more seconds, or we'll get to the end here? I mean, we could take this, right, and then divide both sides by the sum of these two masses, and that would give us this part of the equation divided by these masses together, right, just to get VF by itself, right? I mean, we could do that, but as I said, at this point, because there's so many letters and so many subscripts, I would say it's probably easier just to plug the numbers in and solve for V final. All right, questions there? Okay. All right, just to follow up on this problem. this, and then I'll go here. There we go. Okay. So for number 42, it says, if the final speed of the two players is to be 0, should the running back run faster or slower? Simple answer is the running back's going to have to run what? Faster, right? That, in this case here, this still applies, even if we want to end up with a final, or if a final velocity of 0, okay? But for that to be the case, what has to be true? If the final velocity is going to be 0, what happens to the final momentum in this problem? Right? That whole side becomes 0 like this, right? And then what would have to be true about the running back's initial momentum versus the linebacker's initial momentum? They'd be equal but opposite directions, so that when we add them together we get 0, right? And as far as the explanation goes, right, the mass of the running back is smaller than the mass of the linebacker, so, but if their momentums has to be equal, right, that would lead us to a greater, or require a greater velocity. Good there? And then, as far as 43 goes, right, just to follow up on our answer, right, again, if final velocity is going to be 0, that makes the whole side of this equation 0, and even though we've changed the parameters, right, it's still a completely inelastic collision, so we'd end up with mass of running back times velocity of running back initial plus mass of linebacker times velocity of linebacker initial have to equal 0. Okay? And then you can plug in the masses from the previous problem. The initial linebacker velocity is going to remain the same, and then you can just solve for the initial running back velocity, right? Do that real quick. Let's get a number here. All right, go with this one. Questions here? Okay. All right. I know there's a little section down at the bottom of the page, but let's flip over to the next page and let's take a look at the next example. It says a 950 kilogram red car with a speed of 16 meters per second approaches an intersection traveling in the positive x direction. A 1,300 kilogram blue minivan traveling 21 meters per second is heading for the same intersection in the positive y direction. The car and the minivan collide and stick together, producing wreckage that moves at an angle of 61 degrees relative to the positive x-axis. Find the speed of the wrecked vehicles just after the collision. Okay? So, same thing as before, right? If we're looking for speed of the wrecked vehicles just after the collision, it's asking us to solve for v final, right? However, in the description of the problem and looking at the picture, right, we can't do it in exactly the same way that we did the previous problem, even though this is a completely inelastic collision because the two objects stick together, right? Because of the way these objects are moving before the collision, we have to address this in a little bit different way. And that little different way is summarized at the bottom of the previous page. Sorry, I know I get flip and stuff like that, but right. So it says here, okay, momentum conservation or completely inelastic collisions in 2 dimensions. Momentum still has to be conserved, but very similarly to what we did when we were talking about projectile motion or equilibrium in 2 dimensions, right? Momentum, what's that? That one. It's going to be too dark. So here. Momentum conservation is applied in the x and y directions separately. So we need to conserve momentum on the x-axis and conserve momentum on the y-axis. Like I said, it's similar to what we did in projectile motion and equilibrium in 2 dimensions. We have to take care of x and we have to take care of y separately before we can look at them together. All right? So, going back here, right? Mass of the car they gave us was 950 kilograms. And we know that the car's initial velocity, 16 meters per second. Okay. They also told us that there's a minivan. The mass of the minivan is 1,300. And the minivan's initial velocity, 21 meters per second. Good with that info? Now, thing we have to consider, right? The conserved quantity during the interaction is momentum. So if we're going to conserve momentum x and y, we have to figure out what momentum there is before the collision so we can use it after the collision. Meaning that we have, ooh, that is not the shape I wanted. Hold on a second. Elise would probably be laughing at me right now. So we have some momentum of the red car this way before the collision, and then we have some momentum of the blue car before the collision. Ultimately, we're going to end up with these cars moving off like this. Okay? Good there? All right, so first thing we need to do, calculate the initial momentum of the red car before the collision and the blue minivan before the collision. We're going to do that just by doing what? Calculating any momentum. We're just going to go mass and velocity, right? So go ahead and calculate the red car's momentum before the collision and the blue minivan's momentum before the collision. Sure.
11, 15 times
27 something?
Yeah.
Good with those numbers? All right. Just like this little section told us here, right? We need to conserve momentum on the x-axis and the y-axis separately. So, if there is this much momentum on the x-axis before they ran into each other, there has to be that much momentum on the x-axis after they ran into each other. And if there's this much momentum on the y-axis before they ran into each other, there has to be that much momentum on the y-axis after they run into each other. So, let's do this. So, those momentums that we just calculated are going to become what here after the collision? They're going to become components of the purple, which is the final momentum, right? And here, now we have a triangle. We know the two sides of the triangle, so we can calculate what the hypotenuse of that triangle is, right? So go ahead and do that. Like 30 something. Oh, I've had the window open since 9 o'clock this morning. No, I've had the window open since 9 o'clock this morning. So I just closed. Yeah. So no, it's good. Check out this recording when you go home. Guest appearance, Mr. McWilliam. So I should have told him that he was being recorded, but you know. All right. Anybody find the hypotenuse of this triangle yet? You could if you wanted to. You might get a little bit. Are you in radians? That's one thing. Up at the top where it says mode. No, you shouldn't be in radians. Okay. You should get the same, but you should, or at least maybe a little. Yeah, 31,000. Yeah.
You get opposite over.
And you got to make sure you use the right side, right? So this angle right there is the 61 degrees, right? Well, it depends on if you're using blue or if you're using red, right? If you're using,
I did it upside down.
yeah. If you use 27,300, right, divided by 61, divided by the sine of 61, right?
31,000.
Okay. That sounds. Right. That were you good with that? Okay. You could also use Pythagorean theorem to find, do a squared b squared equals c squared, right? Yes, yeah. You guys are the first class that anybody has even brought that up. Everybody else is just like, oh, there's a squared b squared. So now, Krista, we could do this problem even if they didn't give you that 61 degrees in this, Okay. So now, one thing though, is that the end of the problem? No, because that's number that I've written there is what? That's the momentum, right? Momentum is the conserved quantity, but what is it asking you for here? It's asking you for velocity, right? But regardless of the fact of how we calculate the momentum is still m times v. It's still mass times velocity. So to get v here, you're going to have to divide by the mass. But what does it say happens in this problem? The two objects stick together, so from a mass standpoint, what are you going to have to do? Add the two together, right? And what?
1,000.
Boo kilograms. Boo. Don't be scared. And I believe if everything comes out right, when you round to 2 sig dig, you should get 14 meters per second. Does that work? All right. To finish up this problem and then actually do the follow-up on the next page. Sorry, finish up. Does that work? 14? Look at that. All right, to finish up this problem and to do the follow-up on the next page. 61 degrees is the angle that they gave us to work with. Does that make sense based on the numbers that we were given, the information that we were given? I know it's kind of an open-ended question, but 61 degrees is closer to which axis, X or Y? Closer to the y-axis. And knowing that momentum is conserved here, right, which axis starts with more momentum before the collision? Y-axis starts with more momentum before the collision, right, because we're dealing with a heavier object going faster. So does it make sense that the final momentum is closer to the y-axis than to the x-axis in this problem, right? Because we've got to conserve, right? We've got to keep it the same. Along those lines, for the follow-up question, right, it says, if the initial speed of the red car was greater than 16 meters per second, would the angle be greater than, less than, or equal to 61? It's going to be less than 61, right? Going back to this picture, right, if the speed of the red car is greater, that increases this side of the triangle. And if we make the one side of this triangle longer, that brings the angle down, right? And that would be less than 61. Good there? Okay. Just to finish this up, calendar-wise, there is homework assignment on the calendar for tonight. It is labeled as completely inelastic collisions. So all the problems that are on the homework assignment for tonight are all similar to one of the two example problems that we did in class. Either the straight, either one-dimensional problems like we did with the football player, or two-dimensional problems like we did with the cars. Okay. Answers are posted down here at the bottom, so they're there for you. Okay. If you'd like to work on those. Also, we got about 12 minutes left. If you have questions relating to the lab that I gave you guys yesterday, if you want to work on the calculations or whatever, feel free to do that as well. Okay. Good.